All right, let's talk about objects in equilibrium. In the linear sense, that means the sum of the forces equals 0. In the rotational sense, that's got to be the sum of the torques equals 0. So, let's take a look at an object in rotational equilibrium, such as a diving board. So, here's me getting ready to dive off into there, but I'm not dived off yet. I'm just sitting there. How much what's my mass? Let's see, I am the mass of, this is the mass of me, Mr. Lubbs is about 53 kilograms. Nah, that seems a little bit heavy, but it works all right. I'm assuming the mass of the board is functionally 0 for now. All right. And now I have these 3 points. I have my point where I'm attached, I have my adjustment point, and then there's me. Here is F1. How hard is this thing pulling? Here's F2. How hard is that part pulling? What are the forces on the board right there? The length of the board is LB, so the length of the board is 3.9 meters. This distance here, D, is 1.4 meters. I think I'm slightly out of focus. There we go. There it is. So now, F1, F2 equal what? How hard are these two places pushing on the board? Well, let's start with our old favorite, the free body diagram. So, when you're drawing, so the free body diagram, here we go. I've got me pushing down, that's the force of Lubbs. I have this one pushing up, the force 2. Now, if this one's, when I jump, the board's being pushed up right here, but if I don't jump, the board's going to want to flip around. So I'm going to say this one's pointing down as well, F1. So the board is not accelerating up or down, so the sum of these forces have to equal 0. So that means, let's see, we'll make this way positive. So F2 is positive minus F1 minus the force of Lubbs has to equal 0. But now I also have to take torques into account. Excuse me. Because I have length. Now we do draw a torque diagram. Now our torque diagram, the sum of our torques have to equal 0. But now let's draw a torque diagram. This actually has to be a length. So I have the force of Lubbs over here. I have F2 pushing here, and I have F1 here. That torque diagram, I'll write this on our torque diagram, it actually has the lengths built into it. Now I have to pick an axis. Pick an axis of rotation. Anywhere counts. Oops, that needs to be an exclamation point. Anywhere. Here, 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 here. It doesn't matter. So, because the sum of my torques equals 0, well, let's find out what those torques are. So we're going to have the torque due to 1 plus the torque due to 2. Let's see here. Yeah, torque due to 2 plus the torque due to 3. But let's see, the counterclockwise is positive. I need to pick my axis. I'm going to choose it right here. My axis of rotation. So now, that way is positive. So now, the torque due to 1, which way is that, positive or negative? Oh, I have a feeling it's going to go away. F2 is positive. The torque due to Lubbs is negative, because I'm wanting it to go this way, and that's in the opposite direction of that, and it's in the negative direction. So now torques are the force of 1 times the lever arm of 1, or what I was using, R. Is that what I was using? What was I using before? Yeah, R1, sine of the angle between them, plus torque due to 2, which is F2, R2, sine of the angle between them, and minus the force due to Lubbs, radius of Lubbs, sine of the angle between us. Well, F1 is what I'm looking for. Oh, these add up to 0. So, F1 is what I'm looking for. My radius, the distance between where my force acts and the axis, is 0. That's why I picked it that way. And then I have sine theta, and it doesn't matter what the angle is because it's going to go to 0. F2 is what I'm looking for. F2. R2, it's this distance here. This is R2. So F2, that distance is my distance D earlier. That's 1.4 meters. 1.4 times the sine of the angle between them. That is 90 degrees. Sine 90. Ooh, that's 1. Yay! Minus the force of Lubbs, which is the force of gravity, which is my mass, times gravity, times the distance to me, which is RL in this case. It's the length of the board, where if I remember correctly, it'll be 3.9 meters. 3.9, and then the angle between us, which is 90 degrees. 90 degrees. Sine 90, which is 1. So now, let's keep going. I'm going to switch to a pencil here. So I end up with 0 equals 0 plus 1.4 F2 minus mass, which was my mass? 53 kilograms, times G, times the sine of 90, which is 1. Let's knock this out. 530 equals 1.4 F2. So F2 equals 530 divided by 1.4. Wait, did I screw up? Oh, I didn't multiply it by 3.9. 3.9. 3.9, multiplied that out, equals times 3.9 divided by 1.4, and through the magic of me doing this earlier, I end up with 1480 newtons. F2 is pointing up at 1480 newtons. Well, what's F1 equal? Well, if I go back to over here, my sum of my forces, F2 minus F1 minus FL equals 0. So if I move this around, so F2 minus FL equals F1. So I've got F2 equals 1480 minus the force of me, which is 530 times 3.9. No, yeah, 530 times 3.9. 530 times 3.9. Wait, no, 530. Yeah, I don't need that 3.9. Oh, I'm losing it. Think of that. There's somebody mowing their lawn outside. So, 1480 minus 530 then becomes 0. 8 minus 3 is 5. 950 newtons equals F1. So, we combine the free body diagram with a torque diagram, and now we can figure out forces. And now, that should work regardless where it is, and we will do that one in class.